Hi, this is Cubby, the creator of UrbanStats.org, and you are computing population density incorrectly. You might say, well, that's a bold claim. I know how to do density. I passed fifth grade arithmetic. I even got a check plus plus in it. I know how to divide one number by another. But what if I told you that you're defining density incorrectly? What even is density? Well, that's part one. You can see it on the screen. Let's get into it. So, I like to consider myself a bit of an urbanist. I live in an urban area, don't have a car, walk most places, spend between 30 minutes and 15 hours a day on blue sky complaining about zoning. And in urbanist circles, we've got a very particular definition of density, even if it is a bit vibes based, right? New York, dense. Houston, not dense. And here we can see the left one kind of looks like New York because all the houses are grouped together. On the right, we've got something that's like Houston. All the houses are spread apart, right? The people on the left, they can probably walk to their friends, to work, etc. They're not killing the planet, etc. On the right, they're probably taking a car everywhere, probably going out, clubbing polar bears in their free time, etc. Horrible suburbia on the right, good, nice, dense urban area on the left. Another way to look at this is how full a region is. Like, so for example, here, even though both regions have the same kind of density in terms of how closely the things are packed to each other, the one on the left isn't using the whole island, whereas the one on the right is using the whole island, right? So, the island as a whole, you could say, is more dense on the right because there's no half of it being used for, whatever, nature preserve, golf course, who knows what's on that other half. Okay, so now that we've established that density can mean different things to different people, let's talk about what the standard definition of density that you are probably thinking about at the beginning, that is just the number of people in an area divided by the size of the area. What does that measure? So, does it measure how urban an area is? What we've got here is those same two islands from before, where people are grouped together in one and spread out in the other. But they have the same number of people and the same amount of area. So when we compute the density, we look at the left one, 12 people, let's say this circle's 100 area-wise, we'll keep that consistent throughout, and we get 0.12. On the right, same math. Take 12 divided by 100, 0.12. So, no, it doesn't measure how urban an area is at all. Okay, so if standard density doesn't measure how urban an area is, maybe it measures how full an area is. Now, if we look at this example, we can see that the left side is still 0.12, as before, and on the right, there's twice as many people, so we end up with twice the density, as you'd expect. So the standard density is pretty accurately measuring how full a particular area is. There's a caveat here, I'm going to brush past it, but I think that really, more interestingly, what we have here isn't an urban density metric. Okay, so let's work towards an urban density metric. So what's the difference between these? Well, the one on the left is grouped together, the one on the right is spread out. We could also think about it as the one on the left is only using the top half of the island, whereas the one on the right is using the whole island for the same number of people. Now, what happens if we split them up vertically? Well, what we can end up with is a separate computation of the population density for each of the top and bottom halves of each one of them. On the left, we end up with a population density of 0.24 for the top half, because it's the same 12 people, but only divided by 50 this time. And for the bottom half, obviously, 0. Nobody there, empty. On the right, because they're all spread out in both of them, we end up with 6 over 50 for both, which is 0.12 for both. Okay, but this is two numbers, and we want one number, right? Like a single density value. So let's take an average. First, let's weight this average by area. Conveniently, basically this is just taking an average because each one is weighted by 50. So in the first case, we end up weighting it by 50 and 50, and it ends up being the average of 0.24 and 0.00, 0.12. The second one, same deal, 0.12, 0.12, average is going to be 0.12. Now, you'll notice this is exactly the same result for both of them. We didn't get anywhere here, right? Not only is it the same result, this is actually the same calculation. If you weight by area, what you're doing is you're just undoing the division that you just did. So now you're back where you started. This is just a more complicated way of getting to the same result. I'm not just wasting your time here, don't worry, because there's another way to compute a weighted average here. We can weight by population. So in the first case, we end up putting all the weight on the first number, right? We are weighting 12 times 0.24 plus 0.00 times 0. And that means that our final result is 0.24, so it's higher. On the right, however, we end up with putting 6 weight on each of these, so it's a 50-50 like before, and we end up with 0.12 again. Which means that what we've got here is a metric that tells us that the first region, where the things are closer together, is more urban than the thing on the right, which is more spread out. So it's less urban, less dense. We've solved our problem. So this leads us to what we call the Purcell-based definition of population-weighted density. This is a pretty standard technique for computing population-weighted density. It's what you'll find if you look in the literature. On screen are a couple references. And we're following pretty much the approach that they will use. Note that we're using an arithmetic mean and not a geometric mean. I like arithmetic means because I don't like logarithms. But that's another video. How do we put this into practice? Well, first we take our big region, which here is this big square, and we divide it into subregions. Here we're going to divide it into 9 subregions, each of which has its own population. We then compute the density of each subregion, right? So now we've got a density value for each subregion. Then we take the population weighted average of these densities, right? So here we just take p times d for each, add that all up. We then take the p for each, add that all up, and then compute those, divide, get our population weighted density. Okay, so we've got a definition, everything's good, we're done, right? Right? Well, so that brings us to what I like to call the Purcell problem. What is the Purcell problem, you ask? Well, the issue here is that the parcels are kind of arbitrary. Before, we split up these islands vertically. But what if we split them horizontally? So now, in this situation, we end up with the 2 parcels for each of the islands actually having 6 people each, which means we end up with a population-weighted density of 0.12 for both of them. The first thing you'll notice is that this completely contradicts our narrative from before, right? We end up with the same population-weighted density for both islands, even though one is more urban than the other. More importantly, what just happened here? We ended up calculating the same metric with a slight subtle difference and got 2 completely different values. That's not the sign of good metric, right? The problem here is that the definition of a parcel is kind of inherently arbitrary, and it really shouldn't matter what parcels we pick for what the density we end up with is. Now, of course, you could say dividing in half. Obviously, the problem here is that that's too big and you should have divided it into smaller pieces. So let's do it. Let's lay down a 1-by-1 grid. Okay, so on the left, we've got all these little houses and they all fit into their little squares, and each of those squares is 1-by-1. So it has an area of 1, and there's 1 person in each square, and those are the only things that have any population, so we end up with a population density of 1? That's way too high, right? That's like 8 times higher than before. That's weird. Okay, but on the right, hopefully we'll get something lower. These aren't even aligned properly to the grid? How do we even calculate that? I guess, okay, well, let's see. We could rearrange the grid a little bit so that each one falls into a square, but then it's also 1. That doesn't seem right. So, what is the parcel problem? The parcel problem is that, well, okay, if we have large parcels, that means that the boundaries matter. But if we have small parcels, that means that the population density increases, that we compute at least. The smaller our parcels get. And actually, you can picture this as the parcels get smaller and smaller and smaller, and let's say we treat each person as existing at a point rather than at a space. The density actually goes to infinity, right? Because you're shrinking down and down and down the parcel that that individual person is in while the population remains 1. That's not a sign of a well-behaved metric. Okay, so let's give up, right? This just doesn't work. Let's go back to using area-weighted density, regardless of how unreasonable and not particularly useful it is for urbanists. But wait, in an extremely unexpected twist that shocked and surprised you, That's not actually the takeaway of this video. I have a solution to this problem. It's called radial population weighted density. Let's get into it. So the idea here is that we put down a radius of a particular size. Now this is a parameter, right? This is an arbitrary parameter that we're picking, but I'll discuss techniques for choosing which parameter to pick, parameter value to pick later on. And what we do here is that we take a circle of that radius and we plop it down around a particular person, in this case a house, and we then compute the density in that particular circle, right? So in this case, we're picking a circle of radius 2.5 units, and we can compute that on the left, this particular house has a local density of 5 divided by pi 2.5 squared, pi r squared, area of a circle, and that gets us 0.25. On the right, when you do the same thing, you end up with a density of 0.05. So it's about 5 times more for that particular house on the left as it is for the house on the right. Okay, and of course we don't just want to pick one house to draw a radius around, right? That would be ridiculous. That would obviously not be representative of the full picture. Instead, what we want to do is draw a radius around every location. And that's what I've done here. I've drawn that same 2.5 radius circle around every location. And we can see here that on the left, we've got a bunch of things that are, 4, some that are 5, some that are 2, some that are 3, as color-coded in the 1, 2, 3, 4, 5 on the left. On the right, they're all 1, right? So every single house is in its own circle with nothing else. And when we compute the actual density values, we find that the one on the left is 0.179 and the one on the right is 0.05, so much, much lower. And I think that makes sense, right? So at this particular radius, if we're looking at this distance, everyone on the right might as well be in their own universe, right? They're kind of all isolated. Whereas on the left, a lot of them are near other people. And the nice thing here is that since it's just a single parameter, we can pick one parameter and just use it universally. But we can, of course, also pick our parameter based on our particular need, right? What are we trying to measure here? So if we want to measure walkability, how far can people walk? Let's say 1 kilometer. Pull that out of the hat. Let's say we want something that's like more neighborhood level. What's like a neighborhood level density? How big is a neighborhood? Maybe 250 meters radius, something like that. Do you think people can walk more? 1 kilometer is a skill issue. How far can true walk-pilled urbanists walk? Well, you could do 4 kilometers. Do you want to? 4 kilometers not enough? 10 kilometers? Okay, I think you're just talking about backpacking at this point. And that's that, a metric of density that actually measures urbanization and actually works and makes coherent mathematical sense. Okay, but here's an issue. That was a little complicated to calculate, right? Like, you can't just get these numbers off of Wikipedia, like population and area, and divide them and compute your value. And of course, this is a bit of a bespoke metric that isn't really used by a lot of people, so you're not going to be able to look up these values for a bunch of locations, right? Well, that's where Urban Stats comes in. Urban Stats is your one-stop shop for information about density at various levels. You can find it at urbanstats.org. It used to be called the density database for like 2 months, and there's a couple people who still call it that. It's very annoying. You can get information on regions like states. Look at that. Population weighted density, 3071 per square kilometer, way higher than the area weighted density. Makes sense. California's got a lot of empty space in it. You can look up local regions like Cambridge, Massachusetts. The city, you can see population weighted density, 7,700. The area weighted density, pretty similar. Cambridge is pretty homogeneous throughout. You can look up zip codes if you like. We have zip codes. But wait, there's more. You can look up all 5 definitions of Los Angeles, from the city all the way up to the combined statistical area. We also have statistics for a bunch of international regions. Specifically, we've got countries, states, urban centers, which are kind of like urban areas but international, and that's true for every country in the world. And we also have a bunch of really detailed stuff on Canada, just like the United States. You can make comparisons between regions. For example, did you know that the Los Angeles urban area is actually denser than the Chicago urban area? Probably you didn't know that, because Chicago has great propaganda online. Let's say you don't like averages. A lot of people don't. A lot of people like to use geometric means for parcel-based population density. Some people like medians, etc. But I think that if you want to do something other than the default mean, which I like for a bunch of reasons, you should just use a histogram, because that gives you the full picture. Like, for example, here, you can see that London has a big peak in the middle, right? It's got a lot of areas that are a little bit dense, not too dense. New York, more skyscrapers, more sprawl. That's the missing middle. Oh, right, I almost forgot. I promised you that you could pick whatever radius you want. Now, of course, it's a little complicated to compute, but we pre-computed a bunch of radii here. So you can go all the way up from 250 meters up to 4 kilometers. I know it's all in metric units. That's because I hate freedom. We also have a bunch of other statistics. That's why it's not called a density database anymore. If you wanted to look up the percentage of people who are gay and cohabiting with a partner in Manhattan, we got that for you. If you want to know the percentage of people who binge drink in Manhattan, we got that for you also. The site also has an excellent daily wordle-like game where you answer questions about various statistics related to geographical regions. Juxtaset, a daily geography game. Okay, so now for the conclusion. Standard, or area-weighted as I like to call it, density does not actually measure urban density in a proper way. Population-weighted density is a fix for this, but parcels, which is what basically everyone else uses, causes additional problems. Radial population-weighted density fixes this, and that's why you should use urban stats as your main source for density information in the United States and abroad. And I'm Cubby signing off. Thanks to Ellie for helping me review part of this presentation. Make sure to leave a comment with your thoughts and like and subscribe and share, please, so that more people can hear the word about correct ways of measuring population density.